Let's talk about distributed inference. One of those topics that sounds intimidating, but once you understand the core ideas, you'll see it come up everywhere in senior AI engineering interviews. And honestly, if you're working with any serious LLM in production today, you're already touching this problem whether you realize it or not. So what is distributed inference? Simply put, it's the practice of spreading a model's computation across multiple GPUs, multiple machines, or both, so that you can run a model that's too large to fit on a single device or serve it fast enough to meet your latency requirements. The moment you're dealing with a 70 billion parameter model or a 405 billion parameter model, a single GPU just doesn't cut it anymore. You're looking at hundreds of gigabytes of weights alone before you even think about activations or the KV cache. That's when distributed inference becomes not a luxury, but a necessity. Now, there are several strategies for distributing inference, and interviewers love to test whether you know the difference between them. The first is tensor parallelism. Here, you split individual weight matrices across multiple GPUs. Each GPU holds a horizontal slice of the weight matrix, does its part of the matrix multiplication in parallel, and then you do an all-reduce operation to sum the results before passing to the next layer. Libraries like Megatron LM pioneered this approach. The key thing to understand is that tensor parallelism requires very fast interconnects between GPUs, because for every single layer, you're doing a synchronization step. If your GPUs are connected over something slow, the communication overhead kills your throughput. That's why you typically use NVLink or InfiniBand within a single node, and you keep tensor parallelism within node boundaries. The second strategy is pipeline parallelism. Instead of splitting within layers, you split across layers. GPU 0 runs layers 1 through 10. GPU 1 runs layers 11 through 20, and so on. You pass activations between stages. This dramatically reduces the communication bandwidth you need. You only communicate the activations at pipeline stage boundaries, not at every layer. But it introduces a different problem: pipeline bubbles. If you're processing one request at a time, most of your GPUs are sitting idle waiting for their turn. The solution is micro-batching. You chunk the input into smaller batches and keep all stages busy simultaneously, like a factory assembly line. Still, pipeline parallelism adds latency, which is why it's better suited for throughput-focused batch inference rather than low-latency interactive serving. The third strategy, and arguably the most commonly used in practice for LLM serving today, is a combination called tensor pipeline parallelism, or sometimes called 3D parallelism when you also add data parallelism on top. VLLM, TensorRTLM, and most production inference engines let you configure both tensor parallel degree and pipeline parallel degree together. Now here's something interviewers often probe on. Why does tensor parallelism require high bandwidth interconnects, but pipeline parallelism doesn't? Walk through the math. In a transformer layer with a hidden size of 8,192, a tensor parallel all-reduce on every layer involves communicating roughly 2 times the hidden dimension times the batch size worth of floats. With a batch of 64 sequences, that's millions of elements per layer per forward pass. Meanwhile, pipeline parallelism only communicates the activations once per stage boundary. So if you have 80 layers split across 4 stages, that's 3 communication events instead of 80. The bandwidth requirement drops by an order of magnitude. This is why Llama 3.170b often runs with tensor parallelism of 4 within a node, and you add more nodes via pipeline or data parallelism. Let's talk about sequence parallelism too, because it's emerging and you'll look sharp if you mention it. Standard tensor parallelism splits the weight matrices, but still replicates certain parts of the computation, specifically the layer norm and the residual stream, across all GPUs. Sequence parallelism fixes this by also sharding the activations along the sequence dimension for those non-attention portions of the network. The result is that your memory footprint scales more cleanly with the number of GPUs, and you can serve longer context windows without blowing up your per GPU memory. Now, production distributed inference isn't just about model parallelism. There's the routing layer too. When you have multiple replicas of the same model for high throughput serving, you need a load balancer that's KV cache aware. If you route a request to a replica that already